Every time you type a card number into a website, it crosses dozens of machines you do not own and cannot see. Your router, your internet provider, somebody's data center. Any one of them could read what passes through. None of them can. I wanted to see exactly why, so I captured my own connection at the point where the bytes leave the machine. Here is what my program handed to the network. A perfectly ordinary web request, with something in it I would rather nobody read. And here is what actually left the network card, one layer down. Same request. That is not a diagram. Those are the real bytes, captured this morning. The card number is in there. It has not been removed or hidden somewhere else. You simply cannot get it out. This video is about why not. Every number in this video came from a real handshake with a real server run on this laptop today. Where I'm interpreting rather than measuring, the screen says so. Start with the problem that had to be solved before any of this could work. To scramble a message so that exactly one other person can unscramble it, you both need the same key. That is what encryption is. But you have never met this server before. You have no shared password with it. And every single thing you send to agree on one is being watched by everyone in between. So how do two strangers agree on a secret number, shouting across a room full of people writing down every word? They don't send it. Each side sends a public value, and then each side independently calculates the same answer from what it kept and what it received. The answer itself never travels. That's the idea behind Diffie-Hellman key exchange, and the analogy people reach for is mixing paint. Easy to combine, very hard to separate again. I counted the bytes. My laptop sent 517. The server sent back nearly 4,000. 4,500 bytes in total, and the key the two of them ended up sharing appears in none of them. Which means you can record the entire conversation, every byte of it, and still not work out the key. That is the whole trick. So what is the padlock in your address bar actually telling you? These are the terms my laptop and that server actually settled on. Transport Layer Security version 1.3, using AES with a 256-bit key. Both sides propose what they support and agree on the strongest option they have in common. It is called HTTPS, but the S is doing all the work. The actual protocol is called TLS. Everything underneath it is the same plain web request it always was. The server also had to prove who it was. It presented a certificate saying this connection belongs to example.com, signed by a certificate authority my laptop was shipped already trusting. That part matters more than people think. Encryption on its own is not enough. You can have a mathematically perfect private line to completely the wrong person. The certificate is the part that stops that. Now back to those bytes, because they are more readable than you would expect, just not in the way that would help anybody. Every encrypted message is wrapped in a small header that stays in the clear. The first byte, 17 in hexadecimal, means application data, then the version, then the length, 92 bytes. So somebody watching the wire knows that you sent something and roughly how big it was. They do not learn a single character of what it said. 75 bytes of request went in, 97 bytes went out. The 22-byte difference is the header you just saw, plus a tag that lets the far end detect whether even one bit was altered on the way. That tag is the part people forget. Encryption stops somebody reading your request. The tag stops them quietly changing the amount you are transferring. Tampering doesn't fail silently, it fails loudly. Which brings us to the part most explanations of this skip entirely. No, and I can show you exactly where it leaks, because I went looking in my own handshake. The very first message a browser sends is called the client hello, and it goes out before any encryption exists at all. I searched my own, all 517 bytes of it, for the name of the site. I found it, in plain text, at byte 127. So your internet provider cannot read what you did on a website. They can absolutely see which website it was. Those are very different promises, and only one of them is what most people think the padlock means. There is a fix for this, called encrypted client hello, and it is slowly being deployed across the web. It was not in use on my connection today, which is precisely why I could find that hostname sitting there in the clear. One last thing worth measuring: what all of this costs you. Opening a plain connection to that server took about 80 milliseconds. Adding the full security handshake took 155, so the padlock roughly doubled the time to get started. But that is a one-off per connection. After that, the connection gets reused, and the encryption itself runs in dedicated instructions built into your processor. It is almost free. Before the answer, the usual honesty. This is one laptop talking to one server on one home connection. Those 80 and 155 millisecond figures are mine. Yours will be different, and most of what they measure is distance, not cryptography. What does transfer is the shape, the header in the clear, the 22 bytes of overhead, and the name of the site you are visiting, sitting in plain text in the very first packet. Those are properties of the protocol, not of my laptop. So, back to the question. It is not a promise that the website is honest or safe, or that it will look after what you send it once it arrives. It is not a promise that nobody knows where you went. It is a much narrower promise than that. Between your machine and that one specific server, nobody read what you sent, and nobody changed it on the way. That is the entire guarantee. Which is not everything, but it is the reason you can type a card number into a laptop on a coffee shop Wi-Fi network and have that be a reasonable thing to do. Thanks for watching.